Good afternoon. This is March 3rd of 2019, and today we're going to talk a little bit about logic statements, and compound statements and how we represent logic. So this is chapter 3.1 in your text, and I encourage you to make sure that you've actually done the reading before coming to class, because what my plan is to actually start doing exercises. We have a quiz tomorrow, but from there on we'll be doing exercises in logic and representing it symbolically, etc. So let me just give you a little bit of an overview, and let's see if we can make some sense out of this. So the name of the game is when you, upon completing this, well, let me not do that. Let me say it from another point of view. The key ideas is to understand statements, what type of statements there are, compound or simple statements, and logical connectives. It is also important for us to understand that quantifiers and be able to identify negations. Now, quantifiers are basically parts of a statement which brings in the true or false remark that is generally done with statements. So understanding quantifiers is important, identifying negations, and identify compound statements. And I identify statements using the words not, and, or, if, then, and if and only if. These are connectors. So I'm not going to spend that much time on the history of philosophy. I think it's a pretty cool subject, and I would encourage you, if you ever get a chance in college, to definitely take a philosophy class or an ethics class. There's some really neat things that you'll learn from that. So here is Aristotelian logic. The ancient Greeks were the first people to look at the way humans think and draw conclusions. Once again, this is more a topic for a philosophy class, but to suffice it to say that Aristotle actually did more to structure logic and understanding how people think than anyone in the classical era. So let me just skip over that and get into the whole business that is at hand. So the first thing we have to understand is, what is a statement and what are logical connectives? So here's a perfect statement. A statement is a way of is a sentence that can be judged either true or false. So, for example, Disney World is in Idaho. Is that true or is that false? That turns out to be false. However, the Rockies play baseball in Colorado. That could certainly be considered true. We will label a statement as being either true or false as a means of assigning a truth value to that statement. So here it is, a statement that can be as a sentence that can be judged either true or false. For example, again, my hair color is black. Is that true or false? Or that your school is in Parker, Colorado. Is that true or false? We can label a statement as true or false as assigning a truth value to that statement. That's going to become more important when we deal with things in 3.2. And so, starting again with a simple statement, a sentence that conveys only one idea can be assigned a truth value. Again, an example would be the Rockies played baseball in Colorado. Is that true? So as an exercise, and something we will do tomorrow, is I want you to come up with a simple statement that is either true or false. So now there are two types of statements. Simple statement is a sentence that contains only one idea, but there's another type called the compound statements, and that is sentences that combine two or more simple statements. So these simple statements. So this simple statement is a single idea, but a compound statement is going to be one or more ideas that are actually connected by a thing called a quantifier. So for example, let's take a look. The Brooklyn Bridge goes over San Francisco. The Mississippi River is the longest river in the US. These are simple statements. And so what I'm going to have you do now, or I'm actually going to have you do in class, is come up with 2 examples of statements of this type. Okay, logic in the English language. If we're going to have compound statements, we're going to have to use something called a connective. These are words such as, and, or, if, then, and if, then, else. Now, the connectives can actually be positive, and as in the case of as, and, or they can be negative, which means we're basically negating. So, and one thing I want you to think about as you're looking at this and we're talking about this is, how does this connect with the unit that we've just finished up on sets? What is, for example, what would be an and in set? What would be an or in sets? So now there's a couple types of ors that we need to deal with. An exclusive or, either one or the other given events can happen, but not both. I can go to Florida or Arizona, but I can't go to both. On the other hand, an inclusive or is one or both of those given events can happen. I can go to Florida or I can go to Arizona. And this can be done in such a way that maybe I'll go to Arizona to begin with, and I'll go to Florida later, or I can go to Florida and then Arizona later. Let me move this out of the way. We will play with more examples of this in the coming section on homework. So now, what does it mean to negate a statement? So I can go, an example would be, I want to go to Florida. The negation of that statement is I don't want to go to Florida. I can go, so a negation of a statement is a change of statement to its opposite meaning. I have brown hair. I do not have brown hair is the negation. The negation of a false statement is always going to be true, and a true statement, the negation of a true statement is always going to be false. We'll do some examples as we go. So now as a consideration, I would like you, we're going to do this tomorrow, is to come up with 2 examples of statements of this type. Make one simple, make one compound, and then come up with the negation. Now, one thing that you might want to keep in mind of is the following. So let ABCD be a set, and let the universal set be all of the alphabet, A through Z. Question: what is the complement of A? Well, A is ABCD, so complement of A is going to be E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Now, here's where it gets a little amusing. What is the statement? It's the first 4 letters of the alphabet. What is the negation of that statement? It is the remaining 22 letters of the alphabet. So a negation would be very much like the complement of a set. So now we get into quantifiers. These are words such as all, none, or no, some, etc. All of these words are quantifiers. All my students have brown hair. So that's a statement. Is it true? The answer is no, it is probably false. I don't remember all your hair colors, but not all my students have brown hair. So that is the negation of that statement. So all my students have brown hair is the statement. Not all of my students have brown hairs. That's the negation. So the Caution is be careful when negating statements that contain qualifiers, because we have to play around with that a little bit to make it work. So a statement, all lakes contain fresh water. The negation, not all lakes contain fresh water. So if I'm going to negate quantified statements, then I have to be careful on how I define those negations. So in the case of all, it would be not all or some. In the case of none, there will be some. So let's say all are, some are not. None are, some are. Some are, none are, some are not, all are. So these are the ways that you would negate a statement that has quantifiers in it. So here are the ways that they kind of flip, and if you look back to that list, you'll notice that they actually cross each other. So here's an example. Write the negation of the statement, some books are novels. So I'll give you a couple minutes and let you do that. Okay, so we have the statement, some books are novels, and we want to write the negation of that statement. The solution, look back on your table of what some is versus the negation of that statement. So the negation of some will be none. Some are, none are. So if we look at the solution to this, there's at least one. The statement some books are novels is the same as at least one book is a novel. This is true. The negation has to be false. The negation The negation of this is no books are novels, which is indeed a false statement. Okay, now let's look at another one. Consider the following problem. All coins have the image of George Washington. What is the solution, meaning what is the negation of this statement? I'll give you a few minutes, let you think about that. Okay, so all coins have the image of George Washington. Remember that the quantifiers are all, none, some, and all, some, or none. So those are the quantifiers. So if I have all coins have the image of George Washington on them, then the solution is this is a false statement. Not all coins have the image of George Washington. For example, the nickel has Thomas Jefferson. The dime has Franklin Delano Roosevelt, and the half dollar has John F. Kennedy, and the penny, of course, has Abraham Lincoln. So all coins have the image of George Washington is a false statement. So we would have to say, if we're going to negate this, is some coins do not have the image of George Washington. Okay, so now, using whiteboards and markers, have your group, so you're going to sit in your groups today, come up with 3 statements with quantifiers and their negation. Alright, this will be something that we will do in class tomorrow. So reminder, use whiteboards and markers, have your group, so to get together as a group, and come up with 3 statements with qualifiers and their negation. Now, another problem, and I think you're going to struggle with this a little bit, is the idea of symbolics. This is the tricky part of the whole logic business, but maybe it's something that you should cover when we talk about algebra. I'm not going to be totally, I'm not going to judgment that, but I am going to say this. Suppose I have a statement that I want to make. Let me move the slide. Whoops, darn it. Leland is a farmer. So if I want to negate that, Leland is not a farmer. Fine. But sometimes we're going to be doing some other operations on statements that are either long, they can be long, or for that matter, they can be short, such as Leland is a farmer. But I just get sick and tired of writing Leland is a farmer every time I'm doing something. So what I'm going to do is I am going to define Leland as a farmer. Leland is a farmer. I am going to make that a statement, I'm going to assign it then to a variable. So let P represent the statement that Leland is a father. So P is equal to Leland is a father. Now I'm going to actually escape the show for a moment and I'm going to look at this particular slide. Leland is a farmer. So if I want to negate that and say Leland is not a farmer, then I can represent this symbolically as well. So I'm going to insert an equation. And let me blow that up so that it actually looks like it's something that's part of this slide. I'm going to say, okay, what is the negation of P? Well, simply put, Leland is not a farmer. So what I can write that as, instead of writing out the entire statement, I can do the following. I can write P. Let me find the symbol on equation editor. Oh boy. Okay. Tilde P equals Leland is not a farmer. So by writing negation P, that's the little tilde here, I can say Leland is not a farmer. So I can basically negate a statement without having to write the entire thing. While this may seem a little overkill for something as simple as Leland is a farmer, when we get into compound statements, it will actually be more convenient. So you'll actually see that in a few moments. So writing a statement as a symbol makes life a little bit easier. There's a little more shorthand and it saves us some time. Now, compound statements. Compound statement consists of two or more simple statements. So Leland is a farmer and has brown hair. So you'll notice that I used both two statements and I separated them by a quantifier. All, none, no, none, and so these are called compound statements. The and, or, if, then, if, and only if are considered connectives. Now, just think about this for a moment again. What does it mean for the union of two sets? What connective do I use for the union of two sets? What word would I use? What connective would I use to define the intersection of two sets? And then we have, so those are two things we're going to be questioning about. The other thing is the if and only if and the if then. For example, I want to go to Florida. If I want to go to Florida, then I must complete my grading. This is another connective. It is what is called a flow diagram connective, if then. The other one, if and only if, I will go to Florida if and only if I get my grades in on time. So that's one way of doing compound statements. So get my grades in on time. I will go to Florida. So I will go to Florida if and only if my grades are done. Okay. So now, not statements. The symbol used in logic to show negation of a statement is the tilde. We already did that. And we read it as not. So Leland is a farmer. The negation, not P, is Leland is not a farmer. And there we have that again. And I actually wrote that in the other slide. So now let's look at a couple other combinations that we need to think about. And what I want you to do while we're looking at this is make a connection between what you did in algebra and sets versus what is done here. Keep an eye out for the similarities for this. So the negation of P is not P. The negation of 1 is minus 1. The negotiation of minus 1 is 1. Okay, so I can use negation whether I'm defining negative numbers or if I'm defining the opposite of a statement. So here's another one, and, which is conjunction. I want you to think about what set operation deals with conjunction. What set element, what set operation corresponds to and? Now, the statement can be read as wedge is the symbol for a conjunction, and it is read as and. So if I were to write P and Q, I can go P wedge Q. A conjunction, well, here it is, P and Q, and Q. So it's written as that upside down V, P and Q. And once again, if you think about it regarding sets, what is an intersection? Let A and B be two sets. Then A intersect B. A intersect B is the set of all elements that are in A and in B. So it can be written as the upside down U, A intersect B, or it can also be written with this wedge, with this top-facing wedge. The other words that can be used in this conjunction are but, however, and nonetheless. So, I went to the barber, however, the barber didn't cut my hair. So let's take a look at one other thing. So here's an example. Write the following conjunction in symbolic form. Kanye West is not on tour, but Kanye West is recording a new CD. Okay, so we want to write a conjunction in symbolic form. Kanye West is not on tour, but Kanye West is recording a new CD. How do we write that out? The solution is if we let T and R represent the simple statements. So T is Kanye West is not on tour. R is Kanye West is recording a new CD. So we let T and R represent the simple statements. T is Kanye West is on tour. R, Kanye West is recording a new CD. In symbolic form, the compound statement is going to be not T and R. So not T and R. So Kanye West is not on tour, but Kanye West is recording a new CD. So now, here is the or statement. The or is a disjunction. So we did the conjunction, or let's put it another way, the intersection. So now let's try the union. The disjunction is represented by the symbol V and is read or. So it is Kanye West is, not jump the gun. So disjunction is symbolized by V and is read as or. So in the book, or will be inclusive, an inclusive or. So the symbolic representation of that disjunction is P or Q. So let's go back just a couple seconds. This is T and Q, T and R. This is T or R. Okay, I want to make sure that's very clear. This is read as or, P or Q. So let's write a disjunction. So let P be the symbol, the statement, Camellia will take chemistry. Q is Camellia will take French. So let's write this in a symbolic form. And let's write it as a disjunction. So Camellia will take chemistry or Camellia will take French. We can write that as P or Q. Okay. So here we go. So P is that, and I think I just did this. So suppose write it with a negation. Camellia will not take French, will not take chemistry, or Camellia will not take French. Solution is not P or not Q. So now, in your groups, and this is the last part of this lecture that I will do, at least for the moment, is in your groups, write one conjunction statement and one disjunction statement, and then translate your statements as symbols. Okay, give you a little bit of time for that. All right, so now we want to look a little bit more at compound statements. If a compound statement contains more than one connective, a comma can be used to indicate which simple statements are grouped together. So we're going to look at grouping now, and we're going to try and translate that into symbolic form. So When we write the compound statement symbolically, the simple statements on the same side of the comma are to be grouped together within a parenthesis. Now, when you see this actually presented to you, you're probably going to think of the different laws that you've dealt with real numbers. So you'll see this again being the same kind of business. So consider P is the dinner that includes soup. Q is the dinner that includes salad. R is the dinner that includes the vegetable of the day. So how do I combine that? So if I write this in symbolic form, let's start with the English translation. Dinner includes soup, comma, and salad or vegetable of the day. Who gets grouped? The first symbol, dinner includes soup, which is P, comes out of the parentheses. Now the and, once again, is the upside down V. So we will use, or the intersection, if you want to call it that. I think that's a good way to put it. And salad or vegetable of the day. Salad or vegetable. Salad or vegetable is going to be the or statement. So we symbolically write this as P and the grouping Q or R. So there's the representation of this thing. Now it should look very similar to what you did with A intersect Q union R. So now let's take another look at it. Write the statement in symbolic form, includes soup and salad or vegetable of the day. The solution P, let's go back. Dinner includes soup and salad or vegetable of the day with the comma. So the symbol R, which includes the vegetable of the day, is outside the grouping. It's written as P and, so that's the symbol here, and Q or R. So now let's change symbolic statements into words. So here's another real life example. Let P, the house is for sale. Q, we can afford to buy the house. That's a little tricky in Denver. And now we just want to write this symbolic statement in words. So P or, is that P and or is that P or? That's P and. P and not Q. So that's written as the house is for sale and we cannot afford to buy the house. So the true statement would have been we can afford to buy the house. The house is for sale and we can afford to buy the house. But since we're negating Q, the house is for sale and we cannot afford to buy this house. Now, one may think about this if we take a look at the commutative law. And I remind you that the commutative, two things commute if A plus B equals B plus A. So now if we were to look at this, how would we write the commutation? So we can afford to buy the house and the house, or the houses, and the house is for sale. So in this case, P, it would be not, we can afford to buy the house would be Q, and the house is for sale, that would be P, so it would be Q and P. So here's another way we can do this. Let's do the negation of both. The house is for sale. We can afford to buy the house. Let's do this in a negation. Not P or not Q. So the solution is that the house is not for sale, or we cannot afford to buy this house. So now let's check one other example. How about if we negate the entire group? So write the statement in words, not the quantity P or Q. Give it a couple minutes. And now let's take a look at it. The solution, we're negating both statements. So it would be the house is not for sale, or we cannot afford to buy the house. So it is false for the house is for sale and we can't afford to buy the house. So we're negating both. So now we turn to the last thing, a conditional. A conditional is an if-then or if and only if statement. So we symbolize that by the arrow. It's read as if-then. If the house is for sale, then we can afford to buy the house. Would be written as if the house is for sale, so if, it would be P arrow Q. The antecedent is part of the statement that comes before the arrow. The consequent is the part that follows the arrow. So if P then Q is symbolized as P arrow Q. So here's an example. P is the portrait. The portrait is a pastel. Q is the portrait is by Beth Anderson. Write the statement symbolically. It would be if the portrait is pastel, then the portrait is by Beth Anderson. If P, then Q. So here we are. The solution would be P arrow Q. So now, what can we do if we are writing this as a negation? Once again, the portrait is a pastel. The portrait is by Beth Anderson. So if I negate, either the portrait is not a pastel. If the portrait is not a pastel, then the portrait is not by Beth Anderson. Or if the portrait is by Beth Anderson, then the portrait is not a pastel. So the solution is Q, if Q, then not P. Okay, let's write another conditional statement. And then we're actually going to try this stuff out. So write the statement conditionally, symbolically. It is false that if the portrait is by Beth Anderson, then the portrait is a pastel. So we're going to write this symbolically. So it is false that the portrait is by Beth Anderson. So we're actually using not Q. The portrait is a pastel. We're keeping that statement as is. So it's if the portrait is not by Beth Anderson, or then the portrait is a pastel. We can write this symbolically as not the quantity Q tends to P. So what did we miss? We missed the comma there. So there's a grouping there. It is false that if the portrait is by Beth Anderson, so here is the principal statement right here. If the portrait is by Beth Anderson, then the portrait is a pastel. We're negating the whole bunch, so it's not the quantity Q, then P. A biconditional statement is symbolized by a double-headed arrow and is read as if and only if. So, if and only if is sometimes abbreviated as IFF. You've probably seen me do that in class a couple of times. So the statement P double arrow Q is read P if and only if Q. So here is an example. Alex plays goalie on the lacrosse team. Q is the Huskies win the Champions Cup. And we want to say P if and only if Q. So we state this as P if and only if Q. Alex plays goalie on the lacrosse team if and only if the Huskies win the Champions Cup. So P if and only if. Alex plays goalie on the lacrosse team if and only if the Huskies win the championship cup. So another way of doing this, let's do another example. Q if and only if, not P. That is written as the Huskies win the champion cup if and only if Alex does not play goalie on the lacrosse team. So Q is left alone and P is negated. The last example is the negation of the group. P if and only, the negation of P if and only if not Q. So let's do that. Not P if and only if Q. That can be, it is false that Alex plays goalie on the lacrosse team if and only if the Huskies do not win the Champions Cup. So we can write this in a statement in this fashion. So it is false that Alex plays goalie on the lacrosse team if and only if the Huskies do not win the Champions Cup. So this symbolic stuff, and there's one table that I want to keep, I'm going to end with this table, is negation. These logical connectives. Negation is not. Symbol form is not P. Conjunction. The upside down arrow. The upside down triangle. And. P and Q. The disjunction. Or. P or Q. And the conditional. If then. P. If P, then Q. Now, I want to call your attention back to sets. So if P is symbolic form of a set, then not P will be the complement of the set. Conjunction and, what does that remind you of? Is that if P and Q are sets, then it's P intersects Q, meaning that an element is in P and it is in Q. The disjunction or written with this upside down V, or P or Q. So if these are sets, it is some element is either in P or Q or both. That's a union right here. The two new ones, if, then. If an element is in a set P, then it must also be in a set Q, and that would be a disjunction. The biconditional is P if and only if Q. So an element is an element of P if and only if it is also an element of Q. So these are the different connectors, the logical connectives, and you can see that this is very similar to what we did with sets way back when. I have included some exercises in this slide set that you're actually going to see and will play around with during class tomorrow. So that's it, and I will upload this to server, and we'll see where things go. So thank you very much.